This is a cool little one that we can do. We've worked out, we did this sort of thing often when we were doing level 2. We'd have some sort of bar suspended by a string and we'd have to work out the torques. Now this is just a cool little thing you can do with centre of mass, where what you basically say is, and I would have said, if we have a bar like this, 2 different lengths, okay, and I said calculate the torques on that, you'd go, okay, well the mass of this one multiplied by that distance, if we call that x2, multiplied by x2 will give you the clockwise torque, and you'd say, well the mass of this one, if we called that second one mass 2, we'll call this mass 1 times distance x1 will give us the anti-clockwise torque, right? Now the cool thing is, what we'd then find, if the masses were pretty similar, then we'd find, which they aren't, this mass would be bigger, right? So, and this distance to the center of it would be bigger, so this anti-clockwise torque is going to be bigger. And then you go, okay, well we can then subtract the clockwise torque and we've got a net torque which is anti-clockwise. That's the slow way of doing it. Once we actually know the center of mass, so we could represent this part of the rod by mass, this part of the rod by mass, in the middle we'd make it if that was uniform. This is a shorter bit of rod, so the mass would be smaller, longer bit of rod, mass bigger. So if we actually found the center of mass of these two objects using that formula, m1x is equal to m2d minus x, then we could find the center of mass of these two masses, and we'd expect it to be, well, it's not going to be midway, it'd be about there. That's where we'd expect it to be. Then, if we calculated that one's anti-clockwise torque, which would then be using this little distance here, plus the combined masses, then that would give us the same answer as when we calculated the 2 separate torques. So it's just a cool way to do that quickly.